Start. Hey, good morning, everyone. Good morning.
Good morning.
Good morning. Hey, how's everybody? I see 8 people currently in participating in the Collaborate. Let me just quickly check how many people are in the discussion board. Let's see, 8 people, and I have. Look, I have only 4 people in the discussion board. 5. So if you haven't, please don't forget to sign into today's forum, right? In the discussion board. You should always remember that that's the first thing you need to do, right? If you in a person-to-person class, as you enter the classroom, the first thing you will need to do is to sign in, right, on the sign-in sheet. Excuse me a second. Got a frog in my throat.
Get signed in, Professor.
So before too late, please don't forget to sign in on the discussion board, right? All righty. So let me just quickly, okay, let me bring up the whiteboard. My pen is. Let's start on you. So in our last class, we talked about the properties of logarithm and why the log is used, or how it can be useful, right? First of all, give me this. How it's useful. Give me a break. Okay, maybe if I bring it down here, it's better. Well, I said, basically the logarithm is very useful in expressing a huge number in a condensed way so that it can be more manageable. And second, we looked at the what's more important is the properties, especially one property of logarithm, which is when you have, let's say, base a log of x, I'm sorry, base a log of x, and if x is if x can be expressed as a raised to n, then that that exponent of n can be brought down, and it becomes like a coefficient. In other words, the power function becomes a multiplicative function. And this is the property. This is a very important property, and this is the property that we need to address our problem. Why? And then, we all know that, log base a log of a is 1, right? And simply this will turn into only n, right? But the thing is, why this is, a useful property to us? Because think about it. Our problem was we had basically, we were able to isolate, only up to this point, right? From the compounding formula, right? Our question is n, right? That's our question. This is our question. And then everything else is known. Future value is known, principal is known, r is known, and n is the only unknown. And how do we isolate this exponent of n? The only way, in other words, this is like z equals x to the y structure. It's no longer a multiplicative function, but it's more like it's no longer a multiplicative function. In other words, it's not z equals x times y. If it is z equals x times y, you can find y simply by dividing z by x, but then it is z equals x raised to y. And how do we solve this for y? The only way we can handle it is by using this property of log. We'll have to use this property of log. Okay? That means we'll have to take the log. In other words, if we take the log, and of course, we need to take the log on both sides, because whatever I do here, whatever I do to the right-hand side, I must do to the left-hand side too. So basically, the right-hand side will be log of x raised to y, and then the left-hand side will be log of z. Then using the properties of log and the problem, using the properties of log, we can rewrite this as y times log of x, right? Then think about it. Now we can easily solve for y, because now it's z equals x times y structure. Now it's right, isn't that right? Now it's z. That's okay. Now it's like z. Let me try. It's still very big. It's still very wide. So let me. Okay. Now it's like z equals x times y structure, right? So then we can easily then, we can solve this equation for y. Then it's going to be log of z over log of x, right? So we can solve for y like that. In other words, then the question is, next, our third question then. Third question is, what would be the base of this log, right? What will be the base of this log? And this is something I have not addressed all this time. Yeah. So the third question is, there are three types of logs, right? And we already know, largely three types of log. I'm not saying, it's only limited to three. Number one, common log. And the common log is the log using 10 as the base, right? Like, log, base 10 log of 1,000, right? And we know this. It's and we know it's base 10 log of 10 to the third power, and it becomes 3, right? Whereas there is binary. So in other words, the limitations of base 10 log, right? Base 10 log is that it's only limited to, I shouldn't say it's only limited to, you can take base 10 log of any number, but it's hard to calculate, mentally calculate it, right? You can have something like base 10 log of 173, but without using the calculator, there's no way you can easily visualize it. But the numbers like, multiples of 10 or powers of 10, you can easily visualize it. So relatively, base 10 log is limited. Now, binary log, second type of log is binary log, and binary log is using 2 as the base. So if 2 is the base, again, the numbers like this is not that difficult, right? That will be log, a base to log of 2 raised to the third power, and that will be 3. Or, again, if the number you're taking log of is powers of 2, like 32, 16, 32, 64, it will be very easy to mentally, of course, you can take binary log of any number, but again, without the calculator, it's hard to calculate it. And therefore, and then the third, and this is the hard part. And the third type of log is called, natural log. natural log. Natural log is the log using Euler's number E as the base. So it can, and then that's why, in our main lecture, there was a huge segment about Euler's number. And if you have studied it well, then you shouldn't have problem understanding it. But I'll need to go over it anyway, because I can't expect that everyone has already studied that well. I mean, although the main lecture videos have already been provided, and they were assigned, a long time ago, and you were supposed to study that, but I can't be sure that everybody has studied it very carefully and thoroughly. And if you did, it's been some time. It's been quite a while. So you must have forgotten. Okay, let me take you to, you see Euler's number, right? Part 1, part 2, that was last available on October 18th. So it was almost like 2 weeks ago, right? So if you studied it thoroughly at the time, even if you did, maybe it wasn't very, it wasn't very easy to understand. It wasn't probably that, digestible. I mean, you need to really have, a good, solid math foundation to understand it. But anyway, the point is, the natural log can be used. Natural log doesn't have any limitations. The natural log doesn't have any limitations, right? In the choice of the numbers it can take log of. And I said, of course, other logs, common log, binary log, you can take log of any number with, this base 10, base 2. But, if you were taking, generally, binary, common log or binary log would generally be for, discrete, discrete numbers, or, finite numbers. In other words, as opposed to that, natural log, you can take log of any number. It's, continuous, basically. Binary log is for the time spectrum that is, continuous time spectrum. But, I'm going to come back to this, Euler's number later, but because I was talking about how it can be used to solve our problem, let me wrap this up first. So natural log can be also written as ln. Of course, that n stands for natural, right? So you can write it this way with base e, or you can write it this way. Okay, you can write it this way. And this is our choice. We're going to use natural log to solve our problem. And then the reason, as I said, if you use common log or binary log, you are generally limited in your choice of the. In other words, think about it. If you take common log of these numbers, so how do you know? I mean, you will take log of, That means if you take the log, you'll take log of fv over p, and in the right-hand side, you'll take the log of 1 plus r raised to n. And then, thanks to the properties of log, the right-hand side can be now turned into n times log of 1 plus r. And then since n is our unknown, and we're to solve for n, we'll simply divide left-hand side by the right-hand side. So it's going to be log of fv over p, the log over log of 1 plus r. Okay, then we can nail the time, right? We can nail n. But the thing is, what kind of log do we use? I mean, is it going to be common log? I said it's going to be natural log. But think about it. If you use common log, that means these numbers, if let's say if it is common log, like base 10, it's quite, then we have a problem. I mean, we have a little concern. How do you know if this number, how do you know what fv over p is going to be? How do you know what 1 plus r is? I mean, are they powers of 10? Are they multiples of 10? I mean, if they are multiples of 10, or powers of 10, rather powers of 10, it will be easy to easily solve it. Of course, it doesn't have to be powers of 10 necessarily, but then we'll be using calculator anyway. But as I said, we don't have to worry about that if we use natural log, because natural log doesn't have any limitations. So basically, the log we are going to use is going to be natural log, which can be rewritten as, so it's going to be base e, right? So it's going to be natural log of fv over p, the natural log of 1 plus r, right? And then, of course, natural log will be calculated by Excel. It's not a big deal. What's important is that you just you need to program this, or you just program is a too gigantic for this task. Just encode it into Excel. In other words, build a formula into Excel, right? Okay. All right, then I'm going to come back to Euler's number later, but let's go to our example, and let's do the let's do the exercise. Okay, let's do the problem. Okay, not that one, but where did it go? So I want you to have this file in front of you, right? I want you to open this file and have it in front of you. This is what we did last time, and we solved, basically R, right? The rate, right? By formula. Now this time, let's do it for n. And of course, n is the, in this case, n is the actual number of compounding, right? And when the compounding frequency is 1, right, t is exactly n. T is n itself, right? Because n is t times m. T times m, that's going to be just, the same thing, right? And previously, this scenario, under this, you have principal of 10K, future value, target future value of 30K, and your timeline is 5 years. Then, what should be the interest rate? We solved for it. But in row 19, now they are flipped. You have 10K, and your target future value is 30K. And currently, the market interest rate is 24.57. And if that's the case, then how many years will it take, right, to reach your target future value? In other words, to grow your 10K to 30K, how many years will it take? Of course, then, using, the formula, right, all we need to do is, natural log of FV over P, close parenthesis, and divided by natural log of 1 plus R, which is here, right? Okay. Then we know the answer already because it's just the row 18, the previous problem, just tweaked, so that this time the unknown would be n. So it should be 5, right? Because we're using the same input. Yeah, it should give you 5 exactly, right? Do you have this file in front of you, everyone?
Yes.
Okay.
Yes.
Only one person. Okay, Jared, and what was that?
The file.
Huh?
I'm trying to find the file.
Didn't you download it last time?
Is it under bond valuation? Nah, never mind. I'll find it.
No. Look, you downloaded it last time. I mean, otherwise you didn't do the exercise last time, right?
Oh yeah.
If you downloaded it, it must be in your download folder.
Okay,
right?
no problem.
Unless you moved it to another folder, or otherwise it's in the time value of money, right? In our topic folder, it will be in the time value of money topic folder, right? But then if you downloaded it, then you must delete all the highlighted cells, right? To work on it, you must. So how about other people? Does everyone have this file in front of you? Jesus, do you have this file in front of you? Jesus, are you there? Jesus?
I have a professor.
Jordan, good. Kenny, do you have this file in front of you? Kenny, are you there? Michelle, do you have this file in front of you? Michelle?
I have it.
Hmm?
I have it.
Okay, great. Natasha, do you have this file in front of you?
Yes, I have it.
That's great. Nolvia, do you have this file in front of you? Nolvia? Let's see. Cora, do you have this file in front of you? Cora? Are you there, Cora? Felicia, do you have this file in front of you? Felicia?
Yes.
Okay. Do you have this file in front of you?
Yes.
Okay, great. Grayson, do you have this file in front of you? Grayson? Grayson? Are you there? All righty. Unless, let's see, some people have dropped something in the chat box. My mic is not working. Okay, that's Kenny. And who else? There were two in the chat box. Okay, if you have it in front of you, I think the first one was not that difficult, right? Now, let's go to row 26, right? Because if the compounding frequency is 4, quarterly compounding, then how many years will it take? Most likely it will be about 5 years, but because compounding frequency is greater, it will take less than 5 years. It should take less than 5 years to get to the same target future value. Just like the last time, I added 2 extra columns so that we can handle the adjustment part outside the formula, so the formula can be simpler, right? So here, maybe I should have also put it into like gray or olive. So basically, we are using the same scenario. If compounding is quarterly and APR is given as 22.59, right? That's what we found last time. The periodic rate has to be 5.65. We solved this first, right? For us to arrive at the same future value, right? Which is, in APR, it's only 22.59, which is less than 24.57 under just annual compounding. So then periodic rate, we already know it's 5 point something, but we can, given the APR, we can find it, and it's going to be 5.65. So then now we're going to take the natural log FV over P divided by natural log of 1 plus R. Okay. And then it's going to give you 20 quarters. Okay. It's actually, it should be 20 quarters. Yes. But, let me make sure. Yeah, it is 20 quarters still. And then it should be 5 years too, because 20 quarters in years, you divide it by M, right? And 5 years. Okay, so this way it is easier to, since the formula is simpler, there is a benefit of maintenance, right? I explained that if the formula is simpler, it's easier to identify the source of the error if ever there is an error, right? So it's easier to fix it. If the formula is complex, then it will be more difficult to identify the source of the error, and will be more difficult to fix it, right? And if you do it, let's say you're not doing it like this. If you do it this way, just then the formula becomes more complex, right? First of all, okay, then you will need to take the natural log of 1 plus future value or present value, right, divided by natural log of 1 plus r, but the rate is not this, right? You must understand. In other words, if you have this, the mind of an engineer, if you have a mind of the structural designer, you know that this is not the periodic rate, and we are dealing with quarterly compounding. So obviously, quarterly rate is not this. Then you will need to make an adjustment, right, to this rate. You will need to divide it by 4, right? And you don't enter 4 manually, right? You don't enter 4 manually. 4 is already given here in column D. It's just covered by this formula. You don't enter it, so you just where it is. It's D21. You enter D21, right? Then it's a quarterly rate or the periodic rate. It's gonna use 5.65, and if you hit enter, you will see 20 there. Because we are dealing with quarterly compounding, it will give you, and we used quarterly rate, it will give you how many quarters it will take. So this is not the answer, because the answer, the question is asking you to give answer in years. So then what do you need to do? I mean, this is something most, people these days, especially younger people these days, are prone to fail. In other words, they don't answer the question directly. If the question is, was A equal to B, or if the question was something like that, then the answer should be either yes or no. Yes, it was, or no, it wasn't. Or if the question was, at what time did X occur? Then, all you need to say is at 3 o'clock, or, the answer is when, right? The answer should address when. Or where did this X occur? The answer should address where, right? But people do not exactly address the point of the question. They just, fumble around. Just like, they just fumble around. My question was it this? Did you see what, I've had very hard time with the students, not answering the point of the question, because, sometimes it was about signing up for Connect, and then, creating your account on Connect, or signing up for Connect Access, and they send me emails. I couldn't see this. I wasn't able to do. And when I ask, did you have your access code? Then they say yes. So did you enter your access code? Then the answer should be yes or no. But then they suddenly go astray. Like, oh, I guess, I guess I know what to do from here on. And then later, then, I get the email again. I couldn't log in. And then I trace it back. And it just turned out if they answered me just directly to the point of the question, then there wouldn't have been any confusion. But there's a lot of confusion because students don't get the point of the question, or answer the point, the questioning point, or the point of the question, or answering no for yes or yes for no, right? So it's very important to understand what is being asked. And here, it's not the actual number of compounding. This is actual number of compounding. But the question is years, time in years, right? Then you should do one step further. Okay, this is, if you understand the mechanism, you will understand that this is quarters, right? Then what do you need to do? You will need to divide quarters by D21, which is 4, and then we'll give you what? Oh, divide. Okay, divide by D20. And we'll give you 5. Okay, so now think about it. If you would you rather do it this way or rather do it this way? I think it is easier to do it this way, right? Because there's less confusing. There's less confusion. There's less confusion because n is the actual number of compounding. So as you use and you have to always use the periodic rate. As long as you use the periodic rate, you will get n. If you get n, then you will convert it into years, right? Unless the problem was asking how many quarters will it take. But the question will be most likely asking how many years will it take. And also, some people might say, why not use Excel's built-in function? But again, you have to have a lot of, also, you should be keen and alert, right? If you are not alert, then you are prone to make a mistake, right? So let's, Excel's built-in function, if you use Excel's built-in function, right? Financial. It will be, we're dealing with n, so it's n period. N, right? N periods. So it's asking for a rate. Okay, enter rate. But is it this? Now, if you're not alert, and if you're not alert, and if you don't know what you're doing, you will just enter this because you're just being a number puncher. You will just punch in the data puncher, right? You become a data puncher and you just punch in the data without thinking. If you're alert, you will be thinking. But the people who don't think are not alert, right? Because think about it, the context in the context of this problem is that the compounding frequency is 4. In other words, it's quarterly compounding. It doesn't have to be explained verbally, right? Actual problems you will see will be all verbal. There will be a lot of verbiage, but verbiage is really pariah because to solve the problem, verbiage is not useful. Verbiage is just nothing but garbage. What you need to do is to sort out the useful information, only the necessary information from the garbage, right? You need to sort it out from the garbage, and you throw away the garbage, right? So, but the problem will be given in verbiage, right? If I'm the one making the exam, I will always put it just like this: lean and mean, lean and mean, no frills, because the narrative is obvious, right? You don't need the verbiage for the narrative. Narrative is a scenario. And what do you think is the scenario? Oh, your principal is 10K. You want to grow it to 30K, right? So 30K is your target future value. And currently the APR is this, right? And compounding frequency is 4 quarterly. Oh, then, the narrative is already fully there, right? Currently market interest rate is this, and the compounding is quarterly, and you want to grow this 10K to 30K. How many years will it take, right? But then if I give, if I give out problems like this, then there will be always some complaint, Professor, I don't understand, what does this mean? I need some words. But are the words, is the verbiage really needed? Is it really necessary? Because without the verb, what's important, even if the problem is given to you in verbiage, you won't be using that verbiage. It will be just what's important, what's crucial. You just need to extract. You need to extract the critical information from it. After extracting critical information, the rest of the verbiage is just garbage. You just throw it away, right? And the critical information is that the principal is 10K. Your target future value is 30K. APR is this, 22 point something. Compounding frequency is 4. All you need to do is just plug in these, data into this template or this model. Of course, then the question is, how many years will it take, right? And if you're alert, you can extract this information, only the critical information, right? Crucial information from it. You won't bother with the verbiage, right? Because it's this narrative is obvious. It's the same narrative. It's always, they give you this input data. There was one input data that's missing. That one input data that's missing is the question. That's the unknown. You solve for the unknown, right? Think about it. In all of these, examples we've done so far, without any verbiage, we knew what is the unknown and what the question is asking for. In this case, all the other input data are given, but future value was missing, so it's asking for future value. And in this example, everything else is given. Principal was not given. Principal was the only thing that was missing. Then the principal is the unknown. That's what we're solving for. And this one, it was, everything else was given. APR was missing. APR is what we're looking for. Here, everything is given. Time is not given. So then we'll need to find time. That's the unknown. But then, it's quarterly compounding. So you have to be flexible. Your mind should be flexible to be able to adjust, right? To be able to make adjustment for that, different context, right? So here, if we use, if you just enter this as the rate, then you're wrong because you're not thinking. If you understand the narrative, you will adjust it by, as you enter this APR, that's not the rate. The rate is always the periodic rate. So you will make that adjustment, right? So it's going to be B21 divided by D21. So that goes in there. There's no payment here. Present value, present value is this, and you always need to enter it as, because it's as negative, because it's cash outflow. And then your target future value is this, and there you go. And it gives you already 20 there. It gives you 20, but this is wrong. This is not yet. Why? Because it's 20 quarters, right? And the question wasn't asking for the answer in quarters. It asked for the answer in years. So here, you still need to use your brain. You cannot just let it.
5 years.
Huh? Yeah, you should. In other words, you should divide it by 4, right? Because it is quarterly, and you should arrive at 5. Okay, makes sense, everyone? Um, hmm? So everyone got the same result. If you got the same result, I think this is the right time to take a break. So it's 11:54. So we'll take a 10-minute break and reconvene at 12:05. Okay, 12:05. All right. All right.
dollar, duct tape.
All right, we're back. We're back. Now, so uh, let's think about, the basis of this whole natural law, because in our last session, right? I mean, before the break, I made a actually, big jump because without explaining, the connection between Euler's number and natural log, I just made a jump, because um, uh, based on, the properties of log, we can, solve that. We can solve that equation for n, but uh, we need to take, natural log and y, and then, y natural log uh, and how the natural log came to be. I mean, how it came about. That part that needed to be discussed. So first of all, before what we need to understand what is Euler's number, because Euler's number is the basis of the natural log, and it's literally the base of the natural log, right? So then, what is Euler's number? Euler's number is named after Euler, the famous, mathematician. There are two German mathematicians that made a great impact to modern mathematics, right? One is Euler and the other one is Gauss. And of course, ancient mathematicians like, mainly Greeks, right? Mainly Greeks, or Egyptians, but Greek world and Egyptian world in those days, in ancient world, were pretty much, mixed, mingled, I mean, whatever the ancient civilization had, right, was all shared within the ancient civilizations, which were, basically in those days, centered around, Aegean Sea, where, now, but since the Middle Ages, since after Middle Ages, it's mainly, German mathematicians that developed, that made, that left lasting legacy to the mathematics. One of them is Euler. It's not pronounced Euler. Some people Euler. Yeah, I mean, it looks like Euler, but it makes me okay. Let me write it again. But you don't have to. You don't have to, pronounce it. You don't have to anglicize it. You don't, and if you pronounce it Euler, that's you have no you have no, let's say, respect for foreign languages, right? And you don't have to you don't necessarily need to speak German, but if someone says in German it's pronounced Euler, you just need to follow it, right? Some people and another German mathematician named Gauss. It's pronounced Gauss. It's not pronounced Gauss, right? And when you can, it's not like your tongue is like strapped. It's not like your tongue is constrained so that you cannot pronounce it as Gauss or Euler, right? And if you heard someone's pronouncing it as Euler and Gauss, there's no reason you can't do it, right? But somehow, some British people, Brits are more open to foreign languages. I mean, they learn basically French, from early days on. So even if they don't speak French, I mean, following how it is pronounced in French, for them it's not a big deal. And some German, they can, without any, they can't, even though they don't speak German, they can't, even though they can't speak German, there's no problem following it, following just the pronunciation. Only in America, especially as you go to the inland, right? Middle America, inland, right? Midwest, or the South, you will find people just nonsensically, stubborn, or I mean, there's nothing to be stubborn about. Why is it so difficult to pronounce it as Euler? Or why is it so difficult to pronounce it as Gauss? But they, something that can be easily done, they stubbornly fail at pronouncing it correctly. Now, so basically, Euler's number was discovered by Euler, hence called Euler's number. Sometimes it's also called, exponential function. It's the symbol for exponential function. Why? So first of all, let's think about it. This is all logic. I mean, so everyone be ready to be logical, okay? So let's say we know this is what we need to, this is what we need to raise to something, right? And suppose we raise this to infinity, right? 1 plus all. Suppose we raise this to infinity. And also, let me make a slide. What is R? R is the periodic rate. So it is, in other words, so let me rewrite the whole thing because this is getting difficult. All righty, I'm sorry about that. That was my phone. Now, in compounding, isn't it? Isn't this the crux of the compounding? Isn't that right? Isn't this the crux of the compounding? Hmm?
Yes.
Basically, yeah, that's the crux of compounding, because you are going to raise it to right? Because periodic rate is the periodic rate, right? In other words, let me, if possible, yeah, nice. That's R, right? That's R, and this is N. Come on, give me a nice round circle. Okay, and let's ignore but let's ignore t, and just if time is just 1 year, right? If time is just 1 year, right? We can ignore this, but depending on what m is, even during 1 year, compounding can happen m times, which is like it could be 12, it could even be 365, right? But I've been telling you, m can go to I've been telling you that m can be any number. I mean, theoretically, it can be by the second. Or what if m goes to infinity? Of course, I told you, practically, daily compounding is the maximum they use. In other words, maximum for all practical purposes, m is no more than 365, right? But theoretically, it can be even by the hour, by the minute, by the second, by the nanosecond, even by the nanosecond. And what is nano? Nano is 9 digits. What kind of number has 9 digits? Billion. So nanosecond means 1 billionth of a second. 1 billionth of a second. And theoretically, if we stretch m to infinity, right? If we stretch it to infinity, it will be, and let's, no matter what APR is, this will be a very small number. And let me, so, so we'll just replace APR by 1, okay? Because it's 1, later we can replace it with anything. We'll replace it by 1, right? And then since m goes to infinity, right? We divide it by m and raise it to infinity. Now let's think about it. Any number, it doesn't have to be 1, but any finite number divided by infinity, what's it going to be? Any number divided by infinity, what kind of number will it be? Anyone?
It would be infinity.
No.
You give the number. Like
It
one
will
of
be a what? First of all, use your logic. Be logical. First of all, infinity means infinitely large number. You divide 1 by infinitely large number, what kind of number will it be? Obviously, it cannot be an infinitely large number because you're dividing
Very small.
1 by very small. Yes, you're right. That's the logical answer. This will be infinitely small number or infinitesimal number. That's if it is infinitely small, it's called infinitesimal number. In other words, very small, close to 0. Right? Isn't it right? That will be close to 0. So then think about it. This number in the parenthesis is just slightly greater than 1. Isn't it right? It's 1 plus infinitesimal number, 1 plus infinitely small number. So it's not exactly 1. It's just slightly, very slightly greater than 1. Now, suppose you're raising such a number to infinity. What's it going to be?
Wouldn't
What's
it
it
still
going
be
to
very
be?
large?
No, it's not going to be a very large number. The thing is, let's think about it. If this is just 1, in other words, if this is perfectly 0, if this 1 over infinity is, let's say it's not, it's just 0, but it's not really 0. If it is just 0, the whole thing in the parenthesis will be just 1, right? And then it will be, no matter what, it will always be 1. You raise 1 to infinity, still 1. It's 1 times 1 times 1 times 1 times, and infinitely times 1, still 1. But the problem is that this is not significantly greater than 1, but just slightly greater than 1. It is like 1.0000000000000, infinitely 0 and 1. You raise it to infinity, it's not going to be a large number. It's just going to be about 2.718. 2.718 something something. Now, so it has a, it will reach some limit, and that was explained in the video. But let me just pull it up. Not the video, but the. So here, I was talking about this video, right, which is in the embedded in the, but it doesn't work that well in the and the PDF file. So now, let me use this file. So here. So suppose, right, this is the $1,000 and the future value with the APR of 6%, 5 years under different compounding frequencies, right? And let me just extend it like. Now, how about 1,000? Right? How about 10,000? How about 100,000? 1 million. Now, what I want you to see here is look at the you see these numbers come to what do I want to show here? Let's see. Oh, let me insert a column. Compounding factor. Let me put a compounding factor here. Compounding factor is ah this is a compounding factor, all right? So that's what and think about it. It's I'm trying to show that eventually, it's 1 plus 1 over, yeah. I'm trying to show that it's gonna be approach 2.718. Let's see, it's 1 over 1 plus r raised to, not n, but, n. N. Something. Yeah, all right. Okay. Why isn't it? Oh, no wonder. The whole thing was. Okay. Yeah. One. that was 1. Okay. Yeah. You see, the more I can do, see, if I do in the example I used, right? Instead of APR, I used 1, right? Think about it. If APR is 1, what does that mean? If APR is 1, that's 100%. Later, we can replace this 1 with any actual APR, but if APR is 1, that means 100%. That means doubling, right? If your APR is 100%, then your money will double every year, right? But then under that assumption, right? Under that assumption, if you increase, so it's actually 1 over m, right? 1 over m. If m increases, right? Now that's 1 million, right? I mean, already from like 10,000, it is already 2.718, and then 100,000, 2.718, 1 million, 2.718, right? If you do more, I mean, it doesn't matter. I mean, let's say 10 million, 100 million. How many zeros are there? 2. Yeah, 100 million. Look, it doesn't go any further, right? It reaches a certain, limit, right? It doesn't increase. I mean, it doesn't. The point is, it's not going to be explosive. It's not going to be exploding. It's not going to be a huge number. It will just approach a certain limit, right? So beyond, like 100,000 is always, 2.718, 2.7. In other words, if you extend it to infinity, if you extend the frequency to infinity, still it's going to be around 2.718 something, something, something. So that number is called Euler's number. Okay, that is called Euler's number. And we don't actually, just like pi, right? I know there on Pi Day, you know what Pi Day is, right? It's not the day when you eat pie. Of course, you can eat pie, but March 14th is Pi Day, right? And on that day, there's a lot of competition about, who memorizes the pi to the longest digit, to the longest decimal point, right? To the longest decimal place. I'm sorry, longest decimal place. But is it really? Is there any meaning? Is there any meaning to memorize? It goes on forever. Pi doesn't stop at some point. It goes on forever. It's irrational number. Such a number is called irrational number, right? There is no exact ratio because it goes on forever. Just like that, Euler's number is also an irrational number. It goes on forever, right? In the movie, I always laugh at the scene where they are trying to prove that they are genius, and then they memorize the pi to the longest decimal place. But what's the point of that? I mean, is it really necessary to? Because pi is you never use that. I mean, if you can memorize pi to the 100th digit, 100th decimal place, 110th decimal place, you will never use it for any calculation because it's already in the computer. You only need to, use the symbol pi to execute any computation. So it's just like that. Euler's number is an irrational number. Movies like, I don't know, it was like maybe Avengers, or some kind of Marvel Comics movie, and this hero was a genius, and he or she can even memorize pi to 115th digit. Or what's the point? That's not a genius. Genius is someone who can use logic, implement the logic, so that it can be, of course, being able to memorize something is is intelligence, but it's not the intellect. Intellect is being able to use that intelligence to solve problem, like devise the solution, right? Memorizing pi to the 115th digit is certainly a sign of intelligence, but it's not necessarily the sign of intellect. Because intellect is like the operating system, right? Intellect is like the operating system. Suppose you have a computer. Your computer has, a very high capacity CPU, right? 8 gigahertz, right? CPU, and your RAM is like 24 gigabytes of RAM. That's intelligence. That's certainly intelligence. You can process a lot of things. Your brain can process a lot of things, a lot of information in a very short period of time, and you can hold a lot of memory. I mean, you can remember a lot of things with it. You can hold a lot of things, a lot of information in your short-term memory. That's large gigabytes of RAM, and being able to process a huge amount of information in a very short period of time. That's like CPU, large capacity CPU. That's intelligence, right? But then without the operating system, right, that devises the mechanism for processing something, that's not, there's no intellect. Intellect is that operating system that can devise a mechanism, right? Organize the structure, right? Organize the system, neatly organize this and efficient system that will put this large capacity CPU and large gigabyte RAM into work to solve the problem. And you need to have a program to run that. An intellect is the ability to write that program. You understand? So in the movie, they show it as a sign of genius, being the ability to memorize pi. There is no point in memorizing this 2.718 something something. Who cares? The point is, why this number reaches a certain limit, right? And then how it arrives at this. So the thing is, when you use, so this is Euler's number. In other words, this just like pi, this is the Euler's number, and nobody uses Euler's number for like this. But Euler's number is then if we use Euler's number as the base of logarithm, right? Let's say base e log of x, which is natural log of x, right? That means we can take log of any number, right? Because why? because the base is something slightly greater than 1, something slightly greater than 1. Uh, so in other words, 1 is meaningless, I mean, as a base, because nothing is power of 1, right? Because 1 squared is 1, 1 squared, 1 cubed is 1, 1 raised to infinity is 1. So nothing can use 1 as the base, but if it is slightly greater than 1, it can be base for any number. Another thing is, if you look into your calculator, let me pull up the calculator, and you can take a look at your phone. Your phone's calculator if you hold it horizontally, right? If you rotate it horizontally, it will turn into a scientific calculator. Or if you, sometimes you can, on your phone, you can, there's a button that will switch between scientific calculator and regular calculator. Here, natural log, here's a natural log, and also here's, EXP, right? EXP is the Euler's number. So suppose you press this N1. Try it. No, I think I should press 1 and EXP. No. How do I exponent? Oh wait, this one E. You see that? You press that. You see that? That's Euler's number. And if you take natural log of Euler's number, so let's do that. Okay, I think I must do this first and then take natural log of that. You should get 1. In other words, if you take the natural log of Euler's number, you should get 1. Why? Because it's like this. You are taking natural log of Euler's number. And what is that? That is basically base E log of E. It will have to be 1. Right? It will have to be 1. Okay? And then we are already out of time. I wanted to show you. Of course, I wish I could show you the phone, but on the phone you will see if you turn it into a scientific calculator, you will see both, right? Natural log and E, Euler's number, right? Okay. So that's all the time we have. So any questions? Any questions so far? Any questions? Any feedback? Any questions?
The
Yeah.
only feedback I would have to say, I would have to continuously redo the whole thing over again so I can make sure I have it.
Yeah. Definitely. As the old saying goes, it takes practice, and practice, right? Practice makes perfect. And one last thing. So the Euler's number, and you don't need to know this just yet, but the Euler's number and natural log are very useful and very critical, very crucial in math and science and finance and economics. Why? Because when we cannot deal with continuous time. I'll talk about that later. Continuous time without natural log and Euler's number. Without natural log, there is no way you can handle continuous time. So yeah, that's it for today. And I will, so today is Wednesday, so I will see you guys next Monday. Have a great afternoon and see you next Monday. Okay, I'll stop sharing, stop recording.
All right,
and
see you,
sign out.
Professor.
Perfect.
All right, take care, everyone. Take care, Natasha and Jordan. Take care.